No, Professor.
Okay, now can anybody hear me?
Yeah.
Yeah, we can hear you.
Okay. Okay, sorry about that. I have a work-provided headphones that has like a little mute button right on the side of the headphone. So if you grab your headphones, once in a while I hit it by accident and it doesn't tell you. There's like no red light or anything. Anyway, okay. Sorry about that. So you can hear me now and we can see the screen?
Yes.
Perfect. Okay, thank you. Alrighty, so tonight we are continuing from our last discussion where we were talking about shear design. And so before we do though, I had some really good questions and I want to make sure that everybody is clear about this. So I thought I would share this with the class because it was a really good question. And the question revolves around if this is a beam and say that I have steel. Try to do this best I can. I'm going to really exaggerate this. So say like you have steel in 2 rows and I'm trying to draw it all in this straight line, but anyway, close enough. What I want to reiterate is that the distance from the centroid of your steel to the top of the beam, that distance there is D. Like so. But if you have 2 rows of steel or more rows of steel, then the distance from the centroid of the lowest layer to the top of the beam, this dimension is actually D sub T. I can't do the sub here, but D sub T. And what is the difference? Now that you've done a few of these homework assignments, now that you've run through this a few times, I think we can appreciate the difference. Anytime that you have an equation that has BD, like the minimum steel is 3 square root F prime C over 60 times BD, that D is this D. It's to the center of all your steel. Your moment equation, where you sum up your moments, that you use D to the centroid of all of your steel. The only time you use D sub T is when you do your code required check for epsilon sub T. So epsilon sub T, which I'm going to just type as E sub T, is equal to 0.003 D minus C over C, right? But in this equation, this is actually D sub T minus C over C. When there was only 1 row of steel, it didn't make any difference. D sub T and D are one and the same thing. But now that we're getting into some of these problems with multiple rows, I wanted to make this distinction between D sub T and D. Okay? And then it was also brought up to me that I just want to let everybody know that homework number 4, if you look at the last problem, homework number 4, which I'm reaching over to grab, that's the one that has the one-way slab and then you got the beams. No, I'm sorry, not that one. Homework problems 1 and 2, where you have a T-beam and on the left side of the T-beam, I drew a dimension line and I labeled it 31 inches. That is D sub T. It's a little tough to see it. It's not meant to be to the bottom of the beam. It's telling you what D sub T is. And then on the right-hand side, you have 3 inches plus 27 inches. So D on the right-hand side is actually 30 inches. I want to make sure everybody saw that and was not confused by what is what. Okay, so do we have any questions on that? Okay, and then before we get started continuing with our lecture tonight, do I have any other questions anybody would like to talk about?
Professor,
Yes.
will we get any homework on compression steel before the midterm so we can practice it at least?
I do not believe so. No, it's too late already, isn't it? Because even if compression steel was on the very next homework, then the test would be 2 days after that. So it wouldn't do you any good to start working on it because you have no input from me. You have no, pardon me, my voice is already going. You would have no feedback from me. So it's already too late for compression steel.
Okay, got it. Thank you.
Any other questions?
Yeah, Professor.
Yes.
This is going back to homework number 3, problem 2, where we had a cantilever beam and we were supposed to find the reinforcing. We were supposed to design the beam for maximum positive and negative moments.
Yes.
So we were supposed to analyze it in using a rectangular beam, like a how do I say? So at the end of the problem, where you check for phi and sub n, we use the full equation, area of steel multiplied by the yielding stress of steel, and then D minus that equation.
Okay.
And we use that because it was we're treating it as if it was just a beam that only had a row of steel on the bottom, right, on the tensile face, correct?
Yes.
And then we just inverted that when it came to the negative moment.
Right.
Right. So why are we allowed to do that when then later on we talk about doubly reinforced beams and we have to account for both top and bottom? So why are we allowed to analyze it? Yeah.
Okay. No, that's a great question. All right. Let me take a minute here and draw out for everybody what I think it is you're asking. So if this is a side view of that beam, and we have a support here, and we have a support like over here someplace, something like that. And then this beam has a moment diagram. I'm gonna have to freehand this one. But the moment diagram goes like that and like that. That's not too bad. Okay, something like that. And then if I'm understanding the question correctly, in the positive moment, you need rebar on the bottom of the beam. And in the negative moment, you need rebar in the top of the beam. Okay, so I think I have 2 parts to the answer to that question. The first part is that theoretically, you could just put the bottom steel where you have positive bending, and you could just put the top steel where you have negative bending. These bars don't have to go all the way out. These bars don't have to go all the way out. And that's going to be a lecture. When is that coming? In a few weeks. But we have a lecture about how you can develop these bars and when you can cut them down. but the first part to the answer to your question is that although this is much more complex than what the intent of the problem was, but you could look at it as in the region of maximum positive bending right here, you didn't have any tension or compression steel. It was all tension steel. And as you can see, it was all in the bottom of the beam. And likewise, where you have maximum negative bending, you may not had any steel in the bottom of the beam, which would be acting as compression steel. You only had tension steel. So that's one way to answer that question, is that there's no discrepancy because I only put the steel where I needed it to be. If I had done an analysis right here where the steels are overlapping, then yeah, I could have had a situation where this is still positive, so the steel in the top would have been acting like compression steel. So does that half of the answer help?
Yeah, definitely.
Okay, great. Now here's the other half of the answer, which is much, much shorter. Yeah. Okay, so the other half of the answer, which is much, much shorter, and let me get rid of those, and let me draw in some more steel. So perhaps the steel I needed for positive bending, I do run it all the way out, and the steel that I need for negative bending, I run it all the way out as well. Here's the other half of the answer. You can always ignore the compression steel. You as a designer, when you're designing a beam, you could ignore that compression steel. And your answer is only ever going to be more conservative than if you had acknowledged the compression steel. Remember the lecture we said about compression steel? That compression steel only really helps you when you're pretty much maxed out on your tension steel, and you need to add more tension steel, but you can't because epsilon sub t is getting too small. That's when adding compression steel really helps. And then I did one example where I ran through the whole compression steel problem. And then I compared it. So if I had just ignored that compression steel altogether, what was the difference? It was only like 7%. So the other half of the answer is, even if you really did have a doubly reinforced beam, you could always ignore the compression steel if you don't really, really need it, and your answer will be conservative.
Okay, that clarifies it. I'll go ahead and review that problem then, but thank you.
Okay, great. Any other questions before we continue in shear design?
Professor, on that same problem, I think I made a mistake by choosing a beam. I think it was like 14 by 20 when I did the positive design.
Uh-huh.
And I chose like 14 by 22 for the negative, but I should have been consistent. Is that correct?
Yes, 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 that is correct. So that's why when you have this situation like what's on the screen, and you have some part of it's in positive, some part of it is in negative, then what you always want to do is, let's see, let's get back to there. Let's just, I totally forget what the numbers were, but let's just throw out some numbers. Let's say the positive was 280 kip feet. And again, I'm just making up numbers. And let's say the negative was minus 360 kip feet. You always start with whichever one of these two is larger in magnitude, because whichever one is the maximum absolute moment, that's the one that's going to determine the beam depth. And then the other one, which is smaller, you're not going to change your beam depth. You're just going to change how much steel you have. Because otherwise, if you don't do that, then what you're going to do is you're going to specify a beam that looks like that. You can't change the top because people get very unhappy when you have a floor that has a big step in it, makes it really hard to roll the pianos around. So the top floor has to remain at the same elevation, So what you're describing is at the negative moment, you determine you need that much depth, but in the positive moment, you only need that much depth. But you're not going to specify a beam that looks like this because, again, people will be coming at you with shovels. You don't want that. So you use the largest moment anywhere on the span to determine your depth. Once you have your depth determined by the practices and the methods that I've given to you, once you determine what that depth wants to be, it's going to be the same depth everywhere on the beam, but in other locations, you can use less steel. That's how those work.
So like for the positive design, if I use, let's say 3 rebar, and then the negative I use 4 rebar, that would be okay as long as it met the requirements.
Absolutely. Yeah.
Okay.
And then I think what I was guiding you towards in the particular homework problem that we're talking about, what I was guiding you towards is the top steel, which is for the negative moment, was 3 number 10s, but the bottom steel, which was for the positive moment, was 3 number 9s.
Okay, thank you.
You're welcome. Anybody else? Any other questions before we move on?
I had one more question, sorry, on the homework 4, the last problem.
Okay.
The ends are kind of not closed off on the flanges. Does that mean that keeps continuing?
It
Like,
yes, it does. It means that there are more beams at 8 feet on center. So it's kind of open-ended. But remember that what's happening in that one-way slab in the illustration for, this is homework number 4, part A, doesn't matter because you're not designing that one-way slab. You're designing the beam that has the 3 number 9s that are going in and out of the page.
okay.
So the influence of the beam that's coming in and out of the page is limited to SW over 2 to the left and SW over 2 to the right. So halfway to the beam on the left and halfway to the beam on the right is the limit of what that beam cares about. It doesn't care about anything going on beyond those points.
Since we're designing for the beam, do we need to use the MU equations that we
No.
have to choose from? No, right?
No.
Okay.
Yeah, this is kind of a continuation of the discussion we were having a little earlier, but for everybody's sake, let me try to explain this again. Okay, so I'm kind of very haphazardly recreating that problem statement. Okay, so we have, in this problem, we have 2 different designs, really. We have the design of this slab. The slab is 3, 4, 5 inches thick. We have the design of this slab, and that slab is spanning from beam to beam. If that was the end, it'd look like that. So this is the deflected shape of this span. And when we did lecture 5 and we talked about one-way slabs, that's what this is. And so the moment in this slab, say like the moment right there in this slab, is determined by WUL squared over something, 11, 12, 16, something like that. Okay, but all those equations that I gave you were for the negative moment at the face, the positive moment and the midspan, so on and so forth. But that's not what this homework assignment is about at all. This homework assignment has nothing to do with that. This homework assignment is the design of this beam. So now, hopefully this will help everybody. and not be more confusing. If I look at this beam from the side, so I'm standing over here looking this way, what I see from the side is the beam, and then this slab is right there. Okay, that's what I see this from the side. And because the problem said that it's simply supported, that means that it is supported here and that it is supported here by definition of the problem. So the one-way slab is bending like this, but the beam, which is in and out of the page, the beam is deflecting like this. So you see what the slab is trying to do really has nothing to do with what the beam's trying to do. They're totally two independent systems. You could have, if I put a big, well, let me change my color. Okay, if I put a big load right here, I could fail the slab. This could fail through and fall through. The beams are fine, but I could fail that slab. Or I could put a big load right here, and maybe that load is right here on the design of the beam, and maybe the slab is perfectly fine to carry that load. You basically distribute the loads to the beams, but once it gets into the beam fails. See what I'm saying? They're independent. They're two separate systems.
Yeah, thanks for putting that into perspective.
Okay, and then, because I'm sure lots of folks are getting confused by this, the other part about this is when I design the one-way slab, my steel, my flexural steel is going this way for the positive moment, and it's going this way for the negative moments, you know, because the slabs have positive and negative moments. But the beam, those reinforcements are shown up as dots because your rebar is always going in the direction of your span. So it's down here, spanning in and out of the page down here. And then if I look at the slab reinforcement, those now are dots because I'm looking at it from the side. See, so the whole system is 90 degrees to each other. The slab is just distributing the load to the beams, and then once it gets into the beams, it turns 90 degrees and heads off to the ends of the beams. Okay, so for anybody on this call, did I make that worse or does that better?
That helped me a lot. I appreciate it.
That's a lot better.
Okay, great. I mean, this is your class, guys. So whatever I can do to help you with this stuff, please ask the questions. And if what I've drawn on the screen confuses somebody else, by all means, please go ahead and ask a question. Okay, is everybody's okay then to start moving forward? I hear a
Yes.
okie dokie from somebody.
Yes, we're okay, I guess.
Okay, all right. Let us move forward. If I can find my eraser. Okay, so just a very quick recap of what we did last time. What we learned last time was that shear design in reinforced concrete is not actually shear design, it's reinforcing against a diagonal tension crack. But in that summation of forces for a diagonal tension crack, we are using the shear diagram to determine the applied shear, that's VU, and your capacity is V sub n is your nominal capacity. Your capacity is made up of a component due to concrete called V sub C, and another component due to your steel called V sub S. And there's code required equations for V sub C. And then there's a different code required equation for V sub S. And then you combine them all together. And then there's a lot of prescriptions about shear ties and their spacings. So even if you have enough steel to satisfy the VVN must be greater than VU comparison, you still have to comply with maximum spacings. And there's various different code formulations that will tell you what your maximum spacings are. Okay, so that's what we talked about last time. And now we're going to put it all together in our first example. Okay, so for this example, I have a beam. D is 22 inches, B is 14 inches. I am given some loads here. I have a dead load of 3 kips per foot, a live load of 1.75 kips per foot. My concrete is 3,000 PSI. My steel is 60 KSI. Concrete is normal weight. And you can assume the ties are number 3 with 2 legs, as it's shown here. This is actually what's known more as a stirrup. It's up to the designer and or the builder if they want to put in hoops, which go all the way around, or if they want to put in these stirrups, which kind of hang off of these top 2 bars here. But doesn't matter to us. We don't care, really, if it's stirrups or hoops. What we have are 2 vertical legs that are helping us resist the shear. So here's my beam. The span is 20 feet long. I have this factored load on it. My factored load is 1.2 times 3 is the dead, 1.6 times 1.75 is the live. That's 6.4 kips per lineal foot. So my RU, this stands for my factored reaction, is 6.4 times my 20 over 2, which is WL over 2 is your maximum reaction. And that's 64 kips at my reaction. So here and here are 64 kips. My VU is not at the end. My VU is not 64 kips. My VU is what the shear diagram says at DN from the ends. So if you want to know what your shear is at some distance in from the end, then the equation is your end reaction minus your W sub U times the distance from the end. So I have 64 minus 6.4 times D is 22, and then I converted it to feet. And that gives you 52.3 kips is my VU at D from the end. So I labeled it here. Here's my RU at the very end. Here's my design VU at a distance D from the end. Any questions about that?
So could you repeat the at the end part? Like what do you mean at D from the end?
Okay. D is 22 inches.
Right.
Okay, so that's defined. We have a defined distance for D. The code says, I can draw it on here. The code says, I don't have to design for this end reaction. It's fairly large. I can go from the end of the beam a distance equal to D.
Oh, okay.
So D is a vertical height, but I can go DN from the end. D is 22 inches, so I go 22 inches from the end of the beam, and I analyze what VU is at that point. That's what the code allows us to do.
Okay.
Okay, so here RU is 64 kips, VU is 52.3 kips because it's in from the end. Okay? So this is my design load. I must show that the beam is strong enough to carry 52.3 kips. So I'm going to start by finding the capacity of concrete alone, VVC. And the reason that you start with V sub C is because there's no unknown variables in that. Everything that you need to analyze V sub C is already known. So we can do that. V sub C is 2 lambda square root F prime C BWD. This is the equation I gave you last time. If I substitute in my values, your key is that it's normal weight. So lambda is equal to 1. F prime C is 3,000. You put that in here. BW is 14. D is 22. Plug them in. You get 33.7 kips. Since VU is equal to 52.3 kips, which is greater than half of VVC, so half, we'll take this times 0.75, which gives you, I don't know, like 25 kips, and then take half of that, you're like 12, 13 kips. Clearly 52.3 is greater than 13 kips. So that means, oh, I did actually run it out. 12.6 kips, good guess. So 52.3 is greater than 12.6 kips. So all that tells you is that shear ties absolutely are required at this location. Okay, remember last time we talked about the code does allow you to discontinue the use of ties. You don't always have to have ties the whole length of your beam, but you can only discontinue them when you get to a point where VU is less than half of VVC, which would be in here someplace, but certainly not here. Okay, so at that checkpoint, at that location, shear ties are required. So let's calculate what the demand is for our shear ties. So I think I presented this equation last time. V sub S is equal to AV FYT D over S. I just rearranged V sub S and S. So I can solve for S, which is equal to AV FYT D over VU minus VVC divided by phi, which is equivalent to VS. And I can plug in all my numbers. AV is the total vertical steel in your shear tie. So because I have 2 legs, I have 2 times the area of a number 3 is 0.11 times 60 KSI. My D is 22. My VU is my 52.3 that I found. VVC is the 33.7 times 0.75. And then I divide by phi, 0.75. And this all equals 8.06 inches. What does that 8.06 inches represent?
The spacing?
It is the spacing of the shear ties, yes. And so you're not going to build it to 8.06. Can you go to 9 inches or do you go to 8 inches? What do you do with that?
9 inches.
You gotta go below, right? 8 inches.
You do have to go below. Because remember, the closer you space your steel, the more steel you're providing. The farther you space your steel away, the less steel you're providing. So this number here is not one of those where you can round up or round down depending on what you're closest to. You always round down. If you round it up, you're being unconservative. You're not providing enough steel. Okay, does that make sense to everybody?
Professor, quick question. The 0.11, you got it from a table, right?
Yes, I did. Yeah.
Okay, perfect. Thank you.
Yeah. Yep, that's the area for a number 3. Okay, now we need to check our maximum spacing. Here's where those prescriptions come in. S max is equal to AV FYT over 0.75 F prime C BW. This is the equation I gave you last time. I plug in all my numbers. 2 times 0.11, 60, 0.75, 3,000 PSI, 14 inches wide. I get 22.95 inches. S max is also equal to AV FYT over 50 BW. And so I plug this in here. Careful that this is 60 KSI, this is 50 PSI. So you got to get your units to match out. And you'll get 18.86 inches. VS required is, we're going to have to calculate this for our next set of requirements. So VS required as opposed to VS provided, what's the difference? Well, say that you round down to 8 inches, then you calculate V sub S based on 8 inches, you're going to get a bigger number than VS required, which is actually based on 8.06 inches. So the code says, for this purposes here, I can just calculate my required VS, which is VU minus VVC over phi, the same term you saw right there. So I plug in the same numbers I plugged in here, and my VS required is 36 kips. I compare this 36 kips to this trigger point. This is a go, no-go kind of decision maker right here. And so I plug in 3,000 PSI, 14 inches wide, 22 inches deep, and this value is 67.5 kips. So what this tells you is that VS required is less than this value. Therefore, this leads you to some conclusions. Therefore, your maximum spacing is either D over 2, which is equal to 22 over 2, 11 inches, or 24 inches. These are the two checks for less than 4 square root F prime C. Remember from last lecture, if this had been greater than 4 square root F prime C, then your maximum spacings would have been D over 4 or 12 inches. So this is kind of a decision maker right here. Okay, so we have 5 different maximum spacings that we just calculated. 1 was based on required strength. 2 was required on minimum steel. 3 was based on minimum steel as well. 4 was based on this maximum spacing requirement. So these are different. This is minimum steel. This is maximum spacing. Both of them prescriptions by the code. And 5 is the last of the maximum spacing prescription. So 806, 2295, 1886, 11, or 24. Which one are we going with?
The 8. So number 1, but rounded down.
Yes, that is absolutely correct. Again, the smaller the spacing, the more steel you're providing. The larger the spacing, the less steel. So of all of these, you must pick the least of them because that's the largest steel demand. And then you need to round down to something that they can build, like 8 inches. Okay, so of the 5 requirements for spacing, 8.06 inch controls, smallest spacing means the most steel per foot. So we're going to use 8 inches for the end region, always round down, never up. Per above, the maximum spacing anywhere on the span is 11 inches. That's the next bracket. See right there, that's the next lowest number. So it doesn't matter what the load was at all. Nowhere in this equation did we have anything to do with V sub C or VU for that matter that had nothing to do with the load. So nowhere on the span are you going to be able to space them any farther apart than 11 inches. So what we're going to do is let's figure out where we can start putting our ties at 11 inches. We can't go to 12 inches, but we can put them at 11 inches somewhere on that span. So we can figure out at what factored load level are we able to drop our ties to 11 inches on center. So to do so, VMN is equal to phi VC plus phi VS. So I can calculate my phi VC is already calculated, has nothing to do with the tie spacing. And then I can figure out how much my phi VS is based on putting my ties at 11 inches on center. And this gives me 51.7 kips. From similar triangles, I can take my total span over 2 and my end reaction of 64 kips is equal to x from the end of the beam over 51.7 kips. I'm sorry, this is x from the center of the beam. I don't think I did that. Let me see if I drew that. I did draw it. Okay. Sorry about that. Okay, so what I'm saying is by similar triangles, the distance from the center where you are 0 to the end is 10 feet. So 10 feet over 64 kips is equal to some x amount over the 51.7 kips. And it turns out x equals 8.08 feet. So what this means is when we get to 1.92 feet from the end of the beam, I no longer need my shear ties at 8 inches on center. I can start placing my shear ties at 11 inches on center because the shear demand has dropped down to a point where number 3 is at 11 will take care of it. So my final shear tie layout can be 4 number 3s at 8 inches and then the balance of number 3s at 11 inches. And it will look like this. Okay, so any questions on this, on the shear design?
Professor, so we always go with the lower number, right? The 8, and we round it down. Like if it's 8.2 or 8.3, we round it down to 8, right?
Yes,
Okay.
exactly right. So let me back up here for a second. Actually, let me just do it this way. Let's see, actually, let me get to my phi VC. There it is. Okay, so 0.75 times 33.7 is phi VC plus 0.75 times 2 times 0.11 times 60 times 22 divided by 8. Okay, so my capacity with number 3s at 8, my capacity, phi VN, is equal to 52.5. Kips. Okay, and then my capacity, it seems weird that it didn't change very much at all. 0.75 times 33.7 plus 0.75 times 2 times 0.11, 60, 22 over 11. Whoa. I think I just found like a major typo in my presentation here. That's crazy. I just got 45.1 kips. Yikes. Okay. I know. I'm mumbling to myself. I'll explain. This number's wrong. At least I think it is. I just calculated, unless this number's wrong. One of these numbers is wrong. VVC, VC is 33.7. No, okay. Don't worry, instructor hasn't lost it. I have a point to make here. Okay, in this diagram here, okay, so the shear demand was 52.3, and the capacity with my ties at 8 inches on center is, actually change that color, is 52.5. So my capacity goes right like that. And then as soon as I drop my ties off to 11 inches on center, then this drops to 45.1, and it goes like that. So what we do in design is we make sure that the shear demand is always under the shear capacity curve. The shear capacity is the red line, the demand is the blue line. Now you're probably looking at that going, well, it ain't. I can see it right there, right? Well, remember that the shear demand goes like that. VU is D out from the end of the beam. So I don't need to worry about the 64 at all. It's the 52.3 that I have to meet. But what about this blue line right there? What happened there? Well, what happened there is I screwed up. And I calculated the wrong capacity for number 3 is at 11. So what that would, in reality, what I would do is I would provide more number 3s at 8 inches on center until I got out far enough that when I dropped it to number 3s at 11, like so, I'm still covered above the demand. Okay, I know that was some mumbling. Did I lose anybody?
I'm lost.
No problem. Where can I find you?
Okay, so we have one that we did with the minimum spacing, and then we have one with the maximum spacing, but the one with the minimum is from the end and the maximum is from the middle. That's where I can't understand what's going on.
Okay. Yeah. No, I get it. I get it. Okay, so let's say I'm trying to think the best way to answer that. Let's start with this. Phi Vn is equal to phi Vc plus phi Vs. Okay? And phi Vc doesn't change. That's a fixed number. And in our case, that number is 25.3 kips. But phi Vs does change. Phi Vs is equal to AV FYD over S. So as I change S, as S gets bigger, phi Vs gets smaller, right? So then what I did was I said phi Vn is equal to 52.5 kips when S equals 8, and phi Vn equals 45.1 kips when S equals 11 inches. Okay, does this all make sense so far?
Yes, everything makes sense so far.
So far, okay, great. So then what I did is I plotted this. So let me change my color so this correlates. So the height of this horizontal line right here is 52.5 kips. And the height of this horizontal line right here is 45.1 kips. So I drew a plot of these two values. And where this break happens is depending on how many number 3s at 8 inches, how far out I carry my tighter spacing. I'm the designer. I determine how far out it goes. So I need to carry out my tighter spacing, which produces 52.5 kips, out far enough so that when it drops to 45.1 kips, it's still higher than VU. Because VN must always be higher than VU at every location on the span. Okay, Jesus, talk to me. Does that help?
Yeah, but why did we get 52.3?
52.3 is VU.
Okay.
That's
But
your
it's still-
demand.
Okay.
So I'm overlaying two plots. The blue line is VU, the red line is VVN.
Okay. Okay. All right. Now I see the visual.
And maybe it helps if I draw from the other side too. You know, when we do this in design, you actually have computer programs that generate plots that look like this. They kind of look like that. And so you can visually look at the plot, and as long as the red line at every location is higher than the blue line, then you're safe. But remember that the blue line actually truncates right there as well. So the total blue line goes there, to there, to there, to here. And okay, so you could just put number 3s at 8 inches on center through the whole span. You could totally do that. And if you did that, then your capacity diagram, the red line, would just look like this. You wouldn't have any drops. But you're kind of wasting steel because you have all this area over here where you're providing way more capacity than you have demand for. So that's why typically in design, we will drop them into tiers so that you're saving some on steel where you don't really need the steel anymore.
Okay, it makes sense now. So pretty much the red line is what we're providing, and the blue line is what we have to like be over a little at least, so it doesn't fail.
Thank you. That's exactly what I was trying
Okay,
to say.
now yeah, that everything like I can visually see it now.
Okay.
Professor, and the way we figure out will we drop to change the number of ties is it's through that similar triangles where you find that distance x
Uh-huh.
from
Yes.
the center.
Yes, from the center. The only thing is I put the wrong number right there. That was my mistake. That number's wrong.
What should it be just to mark it up right now?
Yeah. That number right there should be the 45.1 kips. So if you do that, I could do it real quick here. 10 times 45.1 divided by 64.0 is 7.05. So .05 feet. That's this number right there.
So we have 2.95 feet for the other side.
Right. Exactly. Yes. So now 2.95 times 12 divided by 8. So you really need to put 5 number 3s at 8 inches instead of 4 number 3s at 8 inches. So that would fix that. Okay, if I've heard from about 3 or 4 people who have really good questions, and I really appreciate helping me explain this. But that means I have about 20 people that I have not heard anything from. If you feel like you're lost, please say something now.
Professor, what did you calc just a second ago? 2.95 times 12 over something? Over.
Oh, yeah. Okay, so we just said this is 2.95 feet.
Right.
Okay, so see this number right there? How many ties do I need to provide before I can drop it? Well, that number right there, what I did is 2.95 times 12 inches per foot divided by 8 inches is what I'm providing them at, equals, that's what I did. And that equals 4.43, but you can't provide 4.43 ties, so round up to 5 ties at 8 inches on center. Okay, anybody else on the call who's needs a little help with this? Please ask a question now.
Professor, and for the number 11s, do we do the same formula? It's going to be 7.5 times 12 over 11.
Yes, you could, but you don't need to. Because when they build the beam, what you say is balance. And you just say, I don't care how many number 3s it takes, just fill the rest of that beam with number 3s at a spacing no larger than 11 inches on center. That's kind of the industry standard of how you do it. And also you do it that way because you're going to have, you're putting this detail on a structural drawing, and this detail is going to cover all kinds of different beams that may be varying in different lengths. So you don't want to sit there and figure out how many ties it takes to fill every single different beam on the job. You could have over 200 beams that are all almost identical, but they're different in just a few inches. And you would have to figure out how many ties goes in every one of those. That's just not how it's done. So you just specify, fill the rest of the beam with number 3s at 11, and the contractor will then figure out how many ties they need, and they'll overestimate a little bit, and they'll fill it with the ties as you specify.
Professor,
Yes.
so just to be clear, originally you had calculated the 64 kips at the reactions,
Yes.
and then you used the design shear capacity, which was the 52.3, correct?
No. What I did was I calculated the reaction at 64 kips, and then I used similar triangles to calculate what is the shear at a distance of D from the end of the beam. And that was 52.3 kips.
Got it. So the shear capacity would be 52.5.
Yes.
Okay. So when it dropped from 64 to 52.5, you ran that the red line across, and the distance is 7.05 feet.
No. No.
Or what is that distance?
Okay, and I'm glad you asked. We're talking about 2 different things.
Okay.
Yeah, 2 different things. And I'm sure that it was probably confusing. Let me do this. Let me try to do this. There we go. Okay, and let's go to I don't want to belabor the subject, and we do have another lecture to at least start tonight, which is totally fine. But I don't want to leave this in a confused state. So let's do this. Okay, so I got some room to draw. Okay. So what you said was mostly right, but
It was the distance from where it drops.
yeah, you're kind of looking at two different things. Okay, so you calculate your factored loads, and from your factored loads, you calculate your shear diagram. You create a shear and moment diagram. And actually, technically, this would be like, I can't edit it. Okay, whatever. Let's just look at one end. The other end is the same process. For now, let's just look at the one end. So your factored reaction is R sub U. But the code gives us an allowance. The code says you don't have to design for R sub U. Remember last lecture, if you meet these 5 criteria, which is most of the time you will, you don't design for RU, you design for VU. And what is the difference between VU and RU? VU is from the shear diagram, but it is at a distance here that is equal to D. Okay, so that's what I said, similar triangles. We haven't talked about ties or capacity or anything yet. This is just on the demand side. So what the code says is even though your shear diagram looks like this, they're allowing us to design to a shear diagram that looks like, got the wrong color. That. So that becomes our demand. And this over here is VU. This point is VU high. This point is VU high. We just took whatever VU was at D from the end and truncated it. So this becomes your demand curve. So far, so good?
So far, so good.
All right, great. Now you talk about capacity. So your capacity has to be greater than your demand at every location. So if you were to just, no, I didn't want to do that. If you were to calculate what your shear spacing needs to be and just provide those ties through the whole beam, then what you're going to have is a shear capacity looks something like that. And my capacity is greater than my demand at all locations. Okay, so this point was 52.3. This point is 52.5. Remember, because we were at 8.06 inches and we rounded down to 8 inches. That's why it's so close.
Got it.
Okay, so again, so far so good?
I'm keeping up.
Okay, all right. So this is it. This is the end of it. If you just put your ties at 8 inches on center, then you're done. But what I was trying to elaborate on is that we don't do that in the real world because this is all wasted steel out here and
more
here.
economical, correct?
Yes,
Okay.
exactly right. Okay, so what we do instead of that is we tier them. So we will take our ties out somewhat, and then we can drop it. Like number 3 is at 8 to number 3 is at 11. But if I do it too soon, then I get something that looks like this. and kind of replicate it on this side. Okay, so if the capacity, I'll put some numbers on here so you can see what I'm talking about. If the capacity is 52.5 at number 3 is at 8, and the capacity was 45.8, I think, at number 3 is at 11, then if I don't carry out my number 3 is at 8 far enough, look what happened. I have this region where I've under-designed the beam. The shear right here is higher than my capacity. VU is greater than phi VN. So that's no good. I can't do that. So how do I fix that? The fix is super easy. I just carry out my tighter spacing farther until I have completely covered that region. And that's where I was using similar triangles to figure out where is the VU less than 45.8 so that I've gone far enough out to cover that demand.
That makes perfect sense.
Wonderful. Great. Okay. Anybody else? Any other questions? Okay. So I'm not hearing any more questions, and it's perfectly fine to save this until you've done some homework on it, and then I'll sure you'll have some more questions. We can go back to this. We can talk about this in another lecture, or we can talk about it in office hour. So having said that, let's get out of this one. And this is lecture 8, so let's see if I can get to lecture 9. Okay, lecture 9, cracking and deflection. And we're not going to finish this today, I can guarantee you that, because it has 430 slides. So I'm thinking what we should do is let's take a 10-minute break, and then we'll just see how far we get. What do you think?
Sounds good.
Perfect. Perfect.
All right. Let's meet back, I don't know, 6:15, is that enough time?
Yes, that's perfect.
Okay, great. Let's reconvene at 6:15, and I'll see you in a second. Okay, everybody, we're back. And let's see. Can you hear me now?
Yes, we can hear you.
Okay, great. Okay, so tonight's lecture is about cracking and deflection. Cracking and deflection. So remember from lecture 2, we learned about the cracking moment, MCR, and the modulus of rupture, F sub R, where the cracking moment is equal to the negative of FCR I gross over Y sub T, and the modulus of rupture is equal to minus 7.5 lambda square root F prime C in PSI. We also learned how to find the cracked moment of inertia, I cracked. Today, we're going to look at how to apply these ideas to find the instantaneous deflection of concrete beams. So concrete beams start life off as uncracked, but as construction is completed and the full dead load is applied, cracking will occur. This cracking will decrease the stiffness of the beam, and deflections under the dead load effects will be amplified. So this is kind of just normal everyday concrete design. Concrete basically is designed to crack. The steel doesn't even really do anything much until after the concrete is cracked. So that's fine, and it's an economical way to build buildings. The cracks are not ugly or concerning. If there's designed properly, the cracks will just be hairline cracks that you really have to kind of squint to see them in many cases, but they are there. And what these cracks do is it makes this beam, in terms of deflecting, it doesn't feel like a solid rectangular beam anymore. It has all these points of discontinuity that makes the beam not as stiff as it would have been if it was a solid concrete beam. When the live load is applied, the cracking will progress outward towards the ends of the beam as the moment diagram is increased with increasing load. So the more load you put on there, the more the cracking spreads across the span of the beam. Cracking and other serviceability issues are always evaluated with service loads, not factored loads. So in this section, this topic of cracking and deflections are serviceability issues. We've already determined what the strength of the beam is following everything we've done so far. So we're satisfied that the beam is strong enough, but is it going to, when you evaluate it, is it going to have good serviceability? Or is it going to crack too much? Are the cracks going to be too wide and be concerning? Or is the beam going to deflect too much and not be a good product for the owner in a building to have a bunch of cracks and sagging beams is not ideal. So we evaluate cracking and deflection using service loads, not factor loads. And so we're going to use WDL and WLL instead of WU for the factored. And this is only for cracking and deflection. So basically, a cracking will extend to where the applied moment equals the cracking moment. So remember from the very beginning of this course, we could calculate the cracking moment for a beam. And if this is the moment diagram, then the cracking is going to extend to where the moment is above M cracking, as you can see. And I've labeled this to be the dead load moment diagram. And then the cracking here to the beam, it almost feels like this concrete has been removed from the span of the beam in terms of stiffness. So at the midspan, where the cracks project the highest at midspan, what the concrete that is left, we found that by I cracked. Remember, we calculated how much concrete balances the steel, and that's kind of its point of stabilization. And that's, if you remember, we calculated I crack. Well, I crack kind of represents what the stiffness of the beam is right there at the midspan. I gross is where the beam's not cracked yet, out here beyond the points in the moment diagram where the cracking occurs. So the beam is actually like a non-prismatic beam that is full section, then a descending to a minimum section, back to a full section again. When the beam cracks, the physical shape of the beam acts like some of the concrete is missing, thus reducing the stiffness. The beam can be thought of in a shape similar to above, where at the maximum moment, the moment of inertia is very close to I cracked, and in the uncracked regions, the beam still retains its full section, I gross. When the moment is increased by a live load moment, the cracking extends further out towards the end of the beam. So now the moment diagram is bigger because I've added live load, and the M cracked is now further out, so the cracking extends out further. Spacing of the cracks remains pretty stable. New cracks do not appear between the existing cracks, but the existing cracks will get wider and wider as you add more load. The apparent stiffness of the whole beam diminishes as the load increases. So this shape, the part that is removed, keeps spreading further and further out from the center. If we plot a graph of the maximum moment and the midspan deflection, so this, we're just looking at the moment at midspan and the deflection at midspan, and we plot those, you get a pretty linear relationship up to a point. So if I have, this is the moment at stage A, this is the deflection at stage A. So when we first start adding moment to the beam, M sub A, we get some deflections, delta A. MA is just the maximum moment applied at the stage in question. MA will increase as the load stages progress. So MA is just a placeholder. MA could be the moment due to dead load. MA could be the moment due to dead load and some of the live load. Or MA could be the full dead load plus live load. Okay, so does that make sense? MA is just a placeholder for the stage that you're looking at. At first, the moment deflection curve is linear as the beam is not yet cracked. And the slope of this is the stiffness of the beam, which is the moment of inertia of the gross section and the modulus of elasticity. Okay, now if we increase the load, as the loading increases, the beam will start cracking. So see, we got to M cracking here, and MA is greater than M cracking, so now the beam has cracked. So it went pretty linear up to the cracking, and then once it cracked, the stiffness diminished. So the slope dropped, which means you get more deflection for the same moment. Once the beam cracks, the moment of inertia will abruptly change. This causes the moment deflection curve line to flatten out. So this is the slope of the initial section is I gross EC. The slope of the cracked section is I cracked EC. As you can see, we have two apparent stiffness values, one prior to and one post cracking. having a bilinear relationship between moment and deflection is not too useful for design purposes. It's kind of hard to work with this fork in the road here. It would be better to use one effective moment of inertia that gets us to the same end point. So what if I could draw a moment deflection curve that's a linear line, and it starts in the same point, it ends at the same point. So if we're trying to determine what our deflections are, we don't really care if it took this path or the straight path, doesn't matter. As long as we calculate a moment and it gives us a deflection that's accurate, then we can use this pseudo effective moment of inertia. This is the concept of an effective moment of inertia, I sub e. From the same moment, m sub a, we get the same deflection, delta a, regardless if we use uncracked and then cracked, or an effective moment of inertia that is uniform through the whole motion. Okay, so everybody tracking so far? We still there?
Yeah.
Okay. As the moment increases and the deflections increase, then the portion of the pre-cracked doesn't change, but the post-cracked keeps getting longer. So what that means is I effective changes. So I effective is going to be dependent upon m sub a. The more you apply the moment, the flatter I sub e is going to get. In fact, I can see, okay, see the slope here and the slope here. As this keeps getting larger and larger, this slope is flattening out. So it is dependent. IE is not one IE for the whole range of loading. IE is specific to the load that you're interested in and the deflection at the stage that you're interested in. So we're going to have to recalculate this a few times to get different deflections at different loading stages. As the moment is increased, the effective moment of inertia, I sub e, will need to be recalculated, and so I sub e is dependent on the magnitude of m sub a. If we keep going, this kind of just shows you where this would eventually go. As the moment is increased, eventually the reinforcing steel will start to yield, causing a moment deflection curve as shown. This is not failing just yet. Remember, just because your rebar is yielding does not mean your beam has failed, but it's getting pretty close. So if the rebar starts to yield, then it doesn't take any more moment to increasing the deflection. The deflection just keeps increasing with the same load on it. That's the definition of yielding. And so I sub e really starts to flatten out, and your deflections will get very, very large with the same applied moment. The final stage is for illustration only. No valid design will allow beams to yield under service loads. Yeah, it's just kind of obvious. You don't want beams yielding and cracking and sagging under your design loads. For the effective moment of inertia, we looked at ACI 318, section 24.235, and equation 2435A, otherwise known as the Branson equation. There was a fellow named Branson back in the 60s who came up with this formulation. And this is our equation. The equation has two parts, two terms. One is a fraction of the total, that is I gross, and the other is the rest of the total, that is I cracked. And the way this works is you put in m sub a is the moment at the stage that you're interested in the deflection. You put in m sub cracked. And the larger that m sub a becomes, then the smaller m cracked over ma becomes, and the less influence you have from the gross moment of inertia, And 1 minus that number is more the influence that you get from the cracked moment of inertia. So if M sub A is very close to M cracked, then this is close to 1, and you have the gross moment of inertia. The higher M sub A gets, if M sub A gets much larger than M sub cracked, then this goes to 0, and this goes to 1, and you get closer and closer to I cracked. So the terms of this equation, M cracked, again, is minus the modulus of rupture times I gross over YT, modulus of rupture minus 7.5 lambda square root F prime C. MA is the maximum moment at the load stage in question. Now, when I say load stage, what do I mean by that? It just depends on when are the deflections are you concerned about. So think of like casting a beam on the bottom floor of a hotel, say. I just thought of that because I've been watching them build this hotel right off the 71 freeway for the last 6 months. And the first elevated floor is all concrete, and above that is all wood. So you could have a one load stage would be they poured the beams, they poured the concrete, they waited a few weeks, and they kicked all the shores out. How much deflection does that beam have at that time? Well, M sub A at that time would just be the moment due to the self-weight of the concrete. But then after they kick the shores out, they start building the wood structure above it. And they built this thing like four stories of wood on top of the concrete. So then you could say, all right, well, after they've built up all the wood and they put the roof on and everything, how much deflection does this beam have? And you say, well, at that point, M sub A is the moment due to all dead load. And then you could say, all right, well, now we're going to open the hotel and we're going to have occupancy. And the occupancy is now going to have live load. We're going to put furniture in this building. We're going to have people occupying the building. So if I put my code required live load on my structure, now how much deflection do I have? And then MA would be your dead load moment plus your live load moment. So you see what I'm trying to say? MA is what deflection under what loading are you concerned about? In general practice, for what we do, we actually check it about 5 different times. There's 5 different periods of time where the deflection of whatever it is we're designing is of interest. ACI 318, section 24237, states that I effective may be used for the deflection of simple and cantilever spans. ACI 24236 prescribes that for continuous beams, I effective should be taken as the average of the values found by the equation, this equation here, for the controlling positive and negative moment regions, and you average them. The Branson equation with these cubic functions here was found to match the deflection data best with the nonlinear shape as shown here. So in other words, he went out and loaded up a whole bunch of concrete beams, and he loaded them from the first initiation of cracking until the serviceability limits, and he came up with this equation that, again, in concrete design, you're always talking about models that do the best job of approximating what you're going to get. This equation by no means actually calculates the physical properties of what's happening. It's just a model that seems to work pretty good. And so that's what the code has carried for the last 50 years. Okay, guys ready for example? Anybody still awake?
Yes, we're ready.
Yes.
Okay. So here's my beam. Here's my example beam. I've given you the width, I've given you the overall height. I've given you the depth to the steel, and we have 6 number 8s. It is 4,000 PSI concrete. The steel is 60 KSI, and I have 6 number 8s for flexural reinforcement. My dead load is 1 kip per foot, not including the self weight. My live load is 1.5 kips per foot. The span is 36 feet, and it is assumed to be simply supported, which, again, I've had this question. Simply supported has a very specific meaning whenever I say that. That means that this beam is supported by pins and rollers at the very ends and is spanning in between them. And that tells you how you can calculate the deflections, and it tells you how you can calculate the moments. Okay, what I'm looking for is the deflection for the dead load and for dead load plus live load. By the way, you're never going to find, well, you're never going to have a structure that has only live load on it without dead load. That just kind of makes common sense. You can't take the structure away and still support the live load. So it's always going to be dead load or dead load plus live load. Or you could be asked to find just the live load. Sometimes it's important to note how much is this building going to move after it's all built, it's there, all the dead load deflection has already happened. I want to know how much it's going to move from now on due to people coming in or out, or traffic, or parking, or what have you. For deflection, we're going to use the, this comes from your tables, 5W to the 5WL to the 4th over 384 EI is a common equation for deflection due to linear loads on a simply supported beam. For simply supported beams to find deflections. Okay, solution. I need to calculate I gross. I gross is BH cubed over 12. 20 times 27 to the 3rd over 12. 32,805 inches to the 4th. Modulus of rupture, 7.5 lambda square root F prime C. This is normal weight concrete, as I say here, so that's 1, 4,000. I get minus 0.474 KSI. And remember our first lecture, any concrete in tension is negative, concrete in compression is positive. M cracked is minus modulus rupture, I gross over YT. I plug in the values I just found. Y sub T, it's a rectangular beam, so it's halfway, so 27 over 2. And I get for M cracked 1,152 kip inches, or 96.0 kip feet. Modulus elasticity is 57,000 square root F prime C. So 57,000, 4,000 is 3605 KSI. The modulus for the steel is 29,000 KSI. And we need to find I cracked now. So remember from lecture 2, was it? Or lecture 3? We did how to find the moment of inertia of a cracked section. We balanced the first moments, so we have to transform the steel to an area of concrete and solve. So we need to find the modular ratio. 29,000 or 3,605 is 8.04. So the area of steel is 6 times 0.79, 6 number 8s, is 4.74 inches squared. The transformed area of steel is this times the modular ratio. So 8.04 times 4.74, 38.11 inches squared. Equate the first moments. I have bx squared over 2 is 20 inches x squared over 2 is equal to, so the compression area times x over 2 is equal to the transformed area of steel, times 24.5 minus x, which is here. 38.11 times 24.5 minus x. And I solve for x. And I solve the quadratic. I get 7.94 inches. So if this is 7.94 inches, then I should be able to sum up all this area and find the center of gravity. So I did 20 times 7.94 times 27 is the overall, minus 7.94 over 2. They get the center of the concrete. Plus 38.11 times 2.5 is the distance from the bottom of the beam. Divided by the total area, I get 19.06. If I did it right, then 27 minus 7.94 should be 1906. So that confirms that we have the right section. So then, cracked moment of inertia. I have the concrete in compression. 20 times 7.94 to the third over 12. Parallel axis theorem. 20 times 7.94 times the distance to the neutral axis squared, plus the area of the steel times the distance to the neutral axis squared. 13,788. So I gross was what, 32,000? I cracked is only 13,788. It is dramatically reduced by cracking. So now I'm ready for my equation. So, well, almost ready. I need to find out what MA is. So I need my dead load. It's 1 kip per foot plus the self weight. The self weight is 27 high, 20 wide, 150 pounds a cubic foot, divided by my square inch to square foot factor. And the total is 1.563 kips per lineal foot. So my moment, dead load moment, is WL squared over 8. 1.563 times 36 squared over 8, I get 253.2 kip feet, which is quite a bit more than M cracked. So this beam will definitely be cracked under dead load. My live load moment, 1.5 times 36 feet squared over 8, 243 kip feet. So first we want to look at the deflection delta due to dead load only. Therefore, M sub A is equal to MD, which is 253.2. M cracked over MA, which is this ratio we're going to use here, is 96 divided by 253.2 is 0.379. If this number is greater than 1, then you can use 1. Okay, this is an important thing to note. I've seen it done many times. If your MA is actually less than M cracked, that means the beam hasn't cracked yet. But if MA is less than M cracked and you divide them, then this number is going to be bigger than 1. Don't take a number bigger than 1 and plug it into this equation. You're going to get a moment of inertia bigger than the gross moment of inertia, which is impossible. So don't do that. So if you do this step here and this number comes out bigger than 1, then just use the gross moment of inertia. You can never get an effective moment of inertia bigger than the gross moment of inertia. Okay, does that make sense to everybody? Anybody still there?
Yeah.
Thank you. Okay.
Yes, it makes sense.
All right, so I have this ratio. You don't have to do it this way, but I found it easier. Calculate this, 0.379, and then you plug it in here and here. So I have 0.379 cubed times my I gross plus 1 minus 0.379 cubed times my I cracked. And my effective moment of inertia is 14,823, which, as you can see, is only a bit more than the crack moment of inertia. So it's already cracked pretty good. So now my deflection, 5WL to the 4th over 384 EI. I just plug in all my values. My linear load is 1.563 kips per lineal feet. My span is 36 feet. But notice here, you got to put in this fudge factor because this is kips per foot, this is feet, and this is kips per square inch, and this is inches to the 4th. So the easiest way to fix that is just put 12 to the 3rd, which I think is 1724 or something like that, times this to make all your units come out. And we get 1.105 inches for our dead load deflection. Next, if we want the deflection due to dead load and live load, therefore, MA is equal to M dead plus M live. 253.2 plus 243, 496. So I go in here and I figure out my cracked to M cracked to MA ratio. 96 over 496 is 0.193. I take that ratio and I can dump it into my equation, same equation. But now my effective moment of inertia is only 13,925. So this is what I was saying earlier. The effective moment of inertia is dependent upon what load stage you're evaluating. With my linear load of 1.563 plus 1.5, 3.063, now I can plug into my equation and I get 2.306 inches of deflection for dead plus live. Okay, you cannot evaluate the live load alone. You cannot plug into this equation your moment just due to live load and get the right answer. Now, why is that? Because the live load will never be on that building all by itself. It's always accompanied with the dead load. And the dead load already pushed the concrete past cracking. So the live load, the entire stage of live load is on a cracked beam. So if you just evaluated the live load alone, you've negated all of the effect of the dead load already cracking the beam. And you'll just have completely the wrong answer. So you do not calculate live load deflection by plugging into this equation. You calculate it by calculating the total dead plus live and then subtract out the deflection due to dead that you found previously to get to your live load. So in other words, your live load deflection is your dead plus live minus just the dead. 2.306 minus 1.105, and the live load deflection is 1.201 inches. Okay, please make a mental note of that. It does not work the other way. You have to do it this way. Do I have any questions so far?
No.
Okay. Example number 2. We're going to repeat example number 1, except that we're going to assume that this beam is cast in with some columns. So it's basically a fixed in condition. So got the same properties here, 6 number 8s, 4,000 PSI concrete, same dead and live load, same span, but we're assuming a fixed in condition. Required, find the deflection for dead and dead plus live. We're going to use WL squared, WL to the 4th over 384 EI. Notice this is not the same. Kind of looks the same, doesn't it? But what happened? I lost the 5. When you have a fixed in condition, you have 1/5 of the deflection of a simple span. So I just want to point that out. This looks like the same from the last example, but it's not. Solution. Okay, so from example, problem 1, we already got the M cracked, I gross, I cracked, and the dead load, and the live load. So all this is the same as example 1. First, we want the deflection due to dead load only, but we're going to need the moments from both positive and negative bending. The positive moments, and I'm getting these from tables, so you can look these up in load tables. The positive moment is WL squared over 24, which is 84.4 kip feet. And the negative moment is minus WL squared over 12, which is minus 168.8 kip feet. ACI section 24.2.36 says that for the computation of MA, you can take the average of M positive and M negative. So I'm taking the average. This is the absolute. So that's 126.6 kip feet. So M cracked over MA is 96 divided by 126.6, 0.758. I can plug it back into this equation. These values don't change. That's I gross and I cracked. And my effective moment of inertia now is 22,070 inches to the fourth. So my deflection is WL to the fourth, 384 EI. I just plug in all the pertinent values. Don't forget your fudge factor here for inches to feet. And I get 0.148 inches for dead load. Dead load plus live load. So now I get my, actually, what did I got the wrong factor. This is live load, and this is supposed to be live load. So the live load moment is 81.0. Live load negative is 162.0 kip feet. Average is the dead load plus the average of the live load is 248.1. Okay, so don't miss this step. I averaged the positive and negative moments from the live load, but I added them to the dead load. So this is my total averaged moment for the dead plus live stage. And so M cracked over MA is 0.387. Plug it back into the equation. And effective moment inertia, 14,890. And I use my equation, put in my effective moment of inertia, and I get a total deflection of 0.431 inches. Live load deflection is then the difference between the two. 0.431 minus 0.148 gives me 0.283 inches of live load deflection. That's quite a difference, huh? Between simple span and fixed.
Much less.
I'm sorry, somebody had a question?
I'm just saying, yeah, it's much less.
Much less, yes. So it's not just fixed has less deflection than simple span. It does. You can see the equation was only 1/5 of it, but it also averaged out the moments so that the beam does not crack nearly as severely. With the same applied loads, the beam had much less cracking, and much less cracking creates much less deflection. So those two examples together give you a pretty good picture of how cracking creates more instantaneous deflection. Do I have any questions up to this point?
What chapter will we find more examples of this?
Oh, good question. Yeah, good question. I'm looking here real quick.
It's chapter 6, right?
That sounds right.
6, 8, I believe. Or 6, 7.
Absolutely right. Yeah. Chapter 6 is serviceability. And we are kind of working through 6.4 is the calculation. 6.5 is effective moment of inertia. And we're going to stop here for the night and pick this up and finish it out next time. But then we're going to start next time with long-term deflections as opposed to instantaneous deflections. What we just did is instantaneous. We're going to pick it up with long-term deflections and finish out chapter 6 next Tuesday. That was a great question. Any other questions?
Yeah, Professor.
Yes.
If you go back one slide, near the end of example 2, where we're finding n sub a, why is it that we're adding the where is it, the average of live plus dead?
Yes. Well, no. It's the dead plus the average of the live. And I was waiting for somebody to ask that. Let me, I owe you a picture. This particular beam that we just did is fixed, like that. So the moment diagram, remember for fixed, for a moment diagram with a linear load is actually going to look like this. That's what the moment diagram looks like. And this is negative moment. And this is positive moment. So what we did, and we did this twice. We did it up here for the dead load. And then we do it again down here for the live load right here. What the code says you can do is average the maximum negative moment and the maximum positive moment. You can add the two together and divide by 2 to get an average between the maximum negative and maximum positive. And the reason why they do that is if I actually look at the beam, those moments are going to cause cracking. The negative moment cracks it up here and up here. And then the positive moment cracks it down here, like so. So they don't directly add to each other, so to speak. So that's what the code says. You can average those. So what I did up here is I averaged the dead load to get to here. And then down here, I took that average dead load, put it here, and then added to it the average live load.
Okay, I see. Perfect. Thank you.
Yep,
Is
no problem.
that a typo, Professor?
Probably.
ML plus the
Yes.
ML is supposed to be ML negative, correct?
Yeah, I got all kinds of typos in this one. Yeah, that one's an L, and then both of these were supposed to be L's. That's
Okay.
an L, that's an L, that's an L right there. And so MA is MD plus the average of the MLs.
And you only did the average. Oh, never mind. You did the average for both the live and dead load. I just saw that.
Correct. Yeah.
Oh.
Professor?
Yeah.
Also for the exam, it's gonna be up to homework 4. I want to make sure. I want to know how to study for it. Is it gonna be enough if we study the homework only?
Yeah, let's do that. Let's say it's going to include everything that we've done for T-beams, but it stops between T-beams and compression steel. It will not be on compression steel, but it will be on T-beams.
On T-beams. And also, is it possible for us to get any analysis problem like the ones we have in the lecture? Or it's gonna be most likely like the homework problems?
The homework problems are kind of half and half design and analysis. You're probably going to be a little more heavy to the analysis side of it because design problems take up a lot more time. I can't give you problems that are going to take a whole bunch of trial and error and iteration. So
Okay.
yeah, that's not to say you're not going to see a design problem, but you're definitely going to have more on the analysis side. And also, please remember, when I say up to T beams, remember what that includes. We've already talked, all the way back from lecture 1. We talked about the analysis of rectangular beams, the design of rectangular beams, one-way slabs, analysis and design of T-beams, but it also includes cracked moment of inertia, M-cracked, modulus of rupture, all of that stuff was covered in lecture 2. So that's not this, and not this that's on the screen, because this is deflections, but we did cover how to calculate gross and cracked moments of inertia.
Thank you.
Professor, from lecture 1 to lecture 6 is on the midterm.
Is lecture 7 when I started compression steel?
Lecture 7 is
Yeah.
yes, compression steel and
Yeah,
design.
Yeah,
Okay.
lecture 8 was shear, lecture 9 is what we're on right now. Yes, that is correct. And I think we're going to have more time on Tuesday. I know you guys got to study over the weekend, so I'm trying to give you some guidelines. That kind of gives you the scope of what the test is going to be, but we'll cover it in a little more finer detail on Thursday after we finish the rest of this presentation.
Okay, thank you so much.
No problem. Any other questions for me before we sign out?
I think we're good.
All right, very good. Everybody have a great weekend. I'm going to stop the recording, and I'll put this on YouTube tomorrow morning. And everybody have a great weekend.
Thank
Have
you,
a good one.
Professor. Have a
Thank you,
great weekend.
Professor.
Thank you.
Thank you, Professor.